morning, everyone. Today we are very happy to have Brian Billings from Boston University, who will tell us about Dolbeault Virasoro algebra and M5 branes.
Yeah, thanks very much for the invitation. Great to be back here at CMSA. Yeah, so a lot of what I say today is joint work with Ingmar Severi and Surya Raghavendran. Cool, so I'm going to get to the title or motivation for the first word in the title of my talk, probably the very last sentence of the talk. But for now, I'll try to motivate some of the main objects. So it starts with this Virasoro Lie algebra, which I want to think about as being the universal symmetry algebra in a two-dimensional chiral formal field theory. Sort of the symmetry that every CFT has by definition. And this is a central extension of the Lie algebra of vector fields on the punctured line, the punctured complex line. So this talk is mostly about higher dimensional, both generalization and enhancement of this algebra. Two different versions will meet of this Virasoro algebra. And the enhancement version is conjecturally connected, and it's becoming much less of a conjecture, as I'll point out from some results in the talk. But this enhanced version is conjecturally a symmetry at the moment of six-dimensional n equals 2, 0 superconformal field theory, which is very ubiquitous superconformal field theory in 6 dimensions, and at least at the level of what's called the holomorphic twist. And time permitting at the end, I'm going to try to relate this back to the AGT correspondence. Sorry if I can close that. Nope, that did not work. Let's try that. Connect to the correspondence of Alde, Gaeto, and Tachikawa, which associates, in part, a six-dimensional superconformal field theory of this type, a two-dimensional CFT. And under this correspondence, this enhanced algebra that I'm referring to, this is the reason I'm calling it enhanced, really does become the ordinary Virasoro. So this correspondence between 6D and 2D CFT, under this correspondence, this enhanced object really becomes the Virasoro, so it deserves to be called an enhancement of this algebra.
Sorry, can you say more about this? The AGT correspondence, you said this enhanced object becomes the Virasoro.
Yeah.
What does that mean? What's the correspondence between that it sends this?
So I'm not utilizing the full power of the correspondence, but part of what goes into this AGT correspondence is an assignment or a functor from the category of six-dimensional 2, 0 CFTs to two-dimensional CFTs. So every 6D CFT has a corresponding 2D CFT. It's what's called the omega deformation of the six-dimensional CFT. So under this deformation, what I'm claiming is that my enhanced object becomes the usual Virasoro symmetry.
You're saying, I don't quite, but the object is not a CFT, the object is symmetries.
Symmetries of a 6D superconformal theory, yeah. So 6D superconformal theories under the omega deformation become CFTs, 2D CFTs.
That, like any symmetry, like are you describing a map between, like what?
Yeah, so I just say like this. I mean, quite literally, the object that I write down, like this enhanced Virasoro algebra, let me just call it Vir twiddle. We can turn on what's called a differential, which is really like an omega background. So this is like an omega background. And what I'm claiming is that this thing is equivalent to just the usual.
Okay.
So, yeah. So under the omega background, if you know what that means, this object becomes the usual Virasoro algebra. But it's really an object that makes sense. This is somehow an object which is very natural from the point of view of what I call the holomorphic twist of six-dimensional superconformal theory. And by construction, then, it's really something which is natural from the point of view of three-dimensional complex geometry. So this is somehow living in the world of 3D complex geometry, and this is something about Riemann surfaces, one-dimensional complex geometry. So there's sort of, at the level of the twist, this AGT correspondence becomes some correspondence between complex 3 dimensions and complex 1-dimensional theories. So I want to start just with some, actually going in that direction, what I mean by higher dimensional Virasoro algebras. And I'm going to choose to focus on a particular appearance of this higher dimensional Virasoro algebra through a higher dimensional version of the famous Siegel-Sugawara construction. So I just want to remind you of this Siegel-Sugawara construction for the very simplest CFT. It's called the chiral boson. And this chiral boson CFT, it's very simple. It's described by a single field as spin 1, conformal wave 1, and it has the following OPE itself. So it's quadratic pole. And there's a family of conformal structures on this object. That is, there's a family of stress tensors given by this formula. And in this formula, there's a parameter, so I call it a family. There's this parameter lambda, for which the central charge depends on in that way. A more invariant way to describe this theory is to think about B. I said it was a spin 1 field. That means you should really think about B as being a holomorphic 1, 0 form on the Riemann surface. This is a global way to think about it. And the fields of this theory that give rise to this vertex algebra, you should think about as being then holomorphic 1, 0. And within this Batalan-Volkovitsky formalism that I use, everything is, I try to resolve all my constraints or conditions, so the condition that this thing be holomorphic can be resolved by this simple Dolbeault complex. So I think about this chiral boson field as being a 1, star form in the sense of Dolbeault forms on the Riemann surface. And what sort of classical structure gives rise to this OPE? Well, within the Batalan-Volkovitsky formalism, that's what's called a shifted Poisson structure. So the point is that this space of 1, star forms on an arbitrary Riemann surface has a rather canonical shifted Poisson structure. And in the parallel way of deformation quantization, the BV quantization of this shifted Poisson structure gives rise to this OPE up here. And you can describe this shifted Poisson structure in the following way. So it's actually a constant shifted Poisson structure. So I can think about it just being a bivector of the appropriate symmetry inside of this vector space. And here I'm just utilizing Serre duality. So I can think about a bivector here as a certain map from the Serre dual of this object to the object. And the Serre dual of this object is 0, star form on the surface. And this bivector is exactly the holomorphic de Rham definition. So that's what's, this is somehow the semi-classical object which is behind this OPE up here. Any questions on that? And as I said, the BV quantization, which I'm going to leave as sort of a black box, you can think about it in the analogy with deformation quantization of a Poisson manifold. The BV quantization of the shifted Poisson manifold gives rise to this vertex algebra, as I said. And I can also glean things like the stress tensor from the point of view of the BV formalism. So for example, that stress tensor that I wrote down above admits the following description, following invariant description now on any Riemann surface, not just on affine space. And it looks like this. So, well, what is the stress tensor? I need to prescribe a current, a noder current for every symmetry. So here the symmetries are behind the stress tensor are conformal symmetries. Infinitesimally, that's just holomorphic vector fields. So I need to tell you a current for every holomorphic vector field. And the one that was behind that formula that I wrote above is the following noder current. So you remember B is a 1, star form. Mu is just a vector, holomorphic vector field. So here, this is the contraction of a vector field. There's no derivatives in this expression. And then that, so this thing is quadratic in B, whereas this thing is linear in B, but that was the same feature that we had above as well. This object here that appears in this deformation is called the Jacobian of a vector field, so that's what appears there. But that'll come up again later. So speaking of Jacobians, there's another Jacobian around, the Jacobian of a surface, Riemann surface. And this is somehow the moduli space which is behind this chiral boson. So I just want to recall that the Jacobian of a Riemann surface is H1 of sigma with real coefficients modulo the lattice, which is H1 of sigma with Z coefficients. And the interpretation of this quotient is a moduli space. It's the moduli of complex structures on the topological trivial line bundle, so the degree 0 line bundle. So this is the moduli of complex structures on the degree 0 line bundle. So it's a component of the Picard variety, zeroth connected component. And the relationship between this Jacobian variety and the chiral boson, well, one of the relationships is that the tangent space at a fixed complex structure of this Jacobian variety can be understood as just global holomorphic one forms. So it's just the tangent space of the Jacobian variety. So that was clearly the thing that we were resolving before. And what this tells you is that the chiral boson is naturally a family over the Jacobian variety. So it's naturally not just a single CFT, but it's a CFT that makes sense in families where you can vary the complex structure on a line bundle. That's one way to think about the chiral boson. And furthermore, when sigma is compact, in which case I can then study what are called the conformal blocks of the chiral boson CFT, what this gives is a line bundle of the Jacobian variety, and you should interpret the partition function of the chiral boson as a section of this line bundle. So it's not actually a function, but in general, it's just a section of this, what's called a determinate line bundle. So this is really just like an abelian version of a story that's maybe more familiar in the context of Kac-Moody algebras. Have you seen that before? Like localization of the moduli of G-bundles that appears in the Langland's program, for example. This is just like the rank 1 version. So we're just studying the zeroth component of the Picard variety. So with an aim about generalizing this to higher dimensions, I want to point out a very natural generalization of this moduli space called the intermediate Jacobian. And the intermediate Jacobian is an object which makes sense actually really for any odd complex dimensional manifold. I'm going to study just the 3-dimensional version for this talk today. Many of what I say can be generalized to arbitrary intermediate Jacobians. But if X is a threefold, for example, then the intermediate Jacobian is analogous to the Jacobian is a certain quotient of now H3 of the threefold with real coefficients modulo the lattice of H3 with Z coefficients. And what's one geometric interpretation for this with maybe an eye towards, if you know anything about these superconformal theories or 5 branes, this word should appear at some point. But one way to think about this intermediate Jacobian variety is as the moduli space of complex structures on the topological trivial holomorphic 2-gerb. And of course I mean abelian here because I don't know what non-abelian gerbs are. The word gerb will never again appear in this talk, so I just wanted to point out that this is sort of one, at least loose connection to M5 branes and 6D superconformal theories where we believe gerbs play a pretty important role. Not holomorphic gerbs, of course, just ordinary gerbs. This is all at the level of the twist, though. I have more precise statements about the relationship between objects that I'm introducing and M5 branes, but this is sort of a loose connection. But nevertheless, the part of my goal is to associate to this moduli space a higher dimensional version of this chiral boson CFT. So that's partly what I want to do. And I'm not going to talk anything about what a higher dimensional vertex algebra is. For me, that ansatz is called a factorization algebra. I'm going to leave factorization algebras out of my talk today. But I just want to say that in the background, you should think about there being a higher dimensional factorization algebra which somehow controls this moduli space in the sense that the chiral boson controls the Jacobian variety. Now, I work perturbatively, and if I look at the sort of formal completion of this intermediate Jacobian, that is, I look at its tangent complex. Now I'm looking at its tangent complex, so this is now a more derived object than what I was looking at before. What you find is, not the cohomology of holomorphic 1 forms, but you find the cohomology of closed holomorphic 2 forms now. So this is in the complex 3-dimensional case. And there's a cohomological shift here as well. So this omega 2 closed is the sheaf of closed holomorphic 2. So this motivates the following definition, an analogy with complex dimension 1. The higher dimensional chiral boson on the complex threefold X is the theory whose fields are these objects here, namely closed holomorphic 2 forms. And I shift by 1 here, and I always like to work, it's easiest for me to say things in terms of sheaves which are actually locally free. So whenever I say closed 2 forms, you should really be thinking that I have this resolution in mind for closed holomorphic 2 forms. And this is a locally free resolution for closed 2 forms, just the way that Dolbeault cohomology is a resolution for holomorphic sections of ordinary 2 forms. So that this arrow here, by the way, when I write this, there's like del bars which are acting here, and then this arrow means the holomorphic de Rham operator. So luckily for us, just like in complex dimension 1, there's actually a BV structure here. That is, this object wants to be quantized. That's what it tells us. That's very important. And the BV structure takes the form of a shifted Poisson bracket, just like it did before. It's again constant, so I can think about it as being some bivector on closed 2 forms, which I can in turn think about as an actual map from less than or equal to 1 forms to greater than or equal to 2 forms. This is the resolution of closed 2 forms I was using before. This is its Serre dual. That's less than or equal to 1. I'm sorry, I can't remove that. But nevertheless, we know there's an operator like this called the del operator. So it's really the same as before. It's like the middle del operator though. Like before, there was just one middle del operator from functions to 1 forms. Now there's still one middle del operator from 1 forms to 2 forms, and that's really like that's the key behind this Poisson structure, this semi-classical structure.
The BV structure is more than just a Poisson structure, right?
Yeah, this is like a classical BV structure. This is a classical limit. So this is just a shifted Poisson structure. And now I'm claiming, actually, shifted Poisson structures, which are constant, always admit canonical BV quantization. There's no obstruction. There's like a canonically defined BV Laplacian that gives a BV structure on this thing. Just knowing that it's constant coefficient tells me that. So it does admit a BV quantization. If you're uncomfortable with the BV formalism, you could also think about this as a theory with a very sort of sick-looking action functional. This sick-looking action functional looks like this. So remember, beta is my notation for a closed 2 form. What appears here is the inverse of the de Rham operator, holomorphic de Rham operator, and del bar. So del bar is there in the way it always is if you've seen some like holomorphic field theory or even topological field theory. The variation of beta will just tell us that whatever object is here is del bar closed, of course, so that's just giving us holomorphicity. The del inverse is very strange. It's somehow letting us, it's sort of a appearance of the fact that my fields are not just 2 forms, but they're actually closed 2 forms. So it's a manifestation of this constraint that I had to impose via this extra differential. The way to make sense of this is, well, beta is a closed 2 form, so at least locally I can find a primitive for it. So I could try to make sense of this action, but that's really a nasty process. The best way to do it is this formalism here. This is just meant to be a heuristic. In dimension 1, by the way, this action also appears. It's the same exact form. So if you think about here, sigma is or the manifold is a Riemann surface. Beta is a 1 form, or B is a 1 form here. So this is something I can integrate, holomorphic 1 form. Similarly, beta is a 2 form here, so it's something I can integrate. Okay, so this looks like, well, to me, it's a pretty naturally defined theory. If you want to take this analogy with the Jacobian variety going up to higher Jacobian varieties, it appears pretty naturally, in my opinion. There's also other motivations for this theory that I just wrote down. So with Engmar-Severi, we showed that the holomorphic twist of the 6-dimensional 1, 0 tensor theory. So this is one of those exotic supersymmetric theories that's not of Yang-Mills type. So that this is a theory which has, for example, or should describe in principle higher gerbs. This tensor is somehow a what's called a chiral 2 form. So it's like a field. It's like a higher gauge field that satisfies some constraint. That terminology is due to Witten. And this beta field, this closed 2 form that introduces nothing but a holomorphic rendition of that object there. So this does have some connection already to 6-dimensional supersymmetry. So I want to, yeah, go ahead.
Just say again what the UV complex is for this theory.
Yeah, so as like the free theory, this is supposed to describe the space of fields right here.
So it's just a 2 form and 3 form.
Exactly. So if you look at physical degree 0, what I have is a 2,1 form and also a 3,0 form. You should think about those as being the remnants of the curvature of the self, or the self-dual or chiral 2 form according to Witten. So it's not all the components of the 2 form, or the curvature of the 2 form, but it's some components that survive this twist. Yeah. The twist is roughly like taking some cohomology. So you don't see everything that was present in the original theory, but you see a lot of it. And this makes sense on any complex 3-fold. The context for supersymmetry is, of course, conformal manifolds. There's nothing conformal here. It's just complex structures.
That complex structure was stronger than
It's just different in dimension 3, so there's not really a relation. I mean, I would say the best relationship is through supersymmetry. So sort of what I'm advocating for here, and I will in the next 2 slides, is that at least for 1, 0 superconformal structures in in dimension 6, after holomorphic twisting, those become exactly just deformations of complex structures. So under twisting, like 1, 0 conformal becomes complex structures. I'll explain more about what I mean by that. So just like we had before in the ordinary chiral boson, we had a stress tensor. So here I claim that this higher chiral boson has also a stress tensor, but it's of this holomorphic flavor. So it has nothing to do with conformal structures anymore, but it has to do with complex structures. And this holomorphic stress tensor is controlled, no surprise, by holomorphic vector fields. So that's what this is, holomorphic vector fields here. That's the sheaf of holomorphic vector fields. And again, because I like to work with vector bundles, I can choose to resolve this by the Dolbeault complex of the 1, 0 tangent bundle. And this is a sheaf of DG Lie algebras. It's a nice flabby sheaf of DG Lie algebras, locally free. And just like before, I claim that given any one of these vector fields, really this is like a derived vector field because I'm taking it to be an arbitrary Dolbeault form. We can find an explicit current, Noether current, just like before, which realizes the natural symmetry of holomorphic vector fields on closed 2 forms. And how do holomorphic vector fields act on closed 2 forms? I only know of one natural way, and that's by the Lie derivative. The problem is the Lie derivative, that's just an action, it's not a current, it's not a Hamiltonian action. I said that there's some Poisson structure in the chiral boson, so I can ask if this symmetry right here is actually Hamiltonian. Does it have a current? And just like before, I claim it does, and it has this form.
Let's say I mu.
Yes, thank you. Next, this is I mu. So I take the 2 form, I contract with the vector field, that gives me a 1 form, and then I can wedge with another 2 form. So I get a holomorphic 3 form here, which I can integrate. So I should say, strictly speaking, this part of the formula only makes sense when I take beta to be honestly del closed. That's the only way that this actually is a noether current. In general, this thing won't be a noether current, namely it won't satisfy the appropriate bracket relation. So actually you have to, if you resolve the condition that beta be del closed, which I was doing before, you actually have to add some L infinity terms here, which they're not so instructive, but I'll just tell you what they look like. So these L infinity terms, they're still quadratic in beta, so it's still like an action, except they involve more vector fields. So this one is like quadratic in beta and quadratic in mu, and this one is quadratic in beta and cubic in mu. And you see that both of these terms have the property that they both depend on this 3 form that I only introduced when I wanted to homologically resolve this condition that I be closed. So this is just like some L infinity nonsense that doesn't really mean much, but it's there if I want to resolve everything that I told you. Okay, so that's this explicit current here. So I want to now unpack more what symmetry these currents actually describe, and that's this higher Virasoro algebra. So classically, this assignment of a vector field to one of these currents that I just wrote down defines a Hamiltonian action of the sheaf of holomorphic vector fields on this thing I'm calling the higher dimensional chiral boson, this thing that looked like closed 2 forms. Quantum mechanically, just like in complex dimension 1 in CFT, there's an anomaly. So in fact, this action does not quantize, but it just quantizes to a projective action. So there's a projective action, meaning that there's some central extension around. And in QFT, that takes the form of a certain anomaly. In CFT, we call that the Weil anomaly. So there's a holomorphic analog of this Weil anomaly. And in fact, I classified all Weil anomalies, of these holomorphic Weil anomalies, in any dimension. They're modeled by what's called local cohomology of holomorphic vector fields, so that's what I'm denoting here. And it takes this explicit form. So if you're on a general complex manifold X, there's some cohomology of X that appears. But if I'm just on flat space, what appears is the cohomology of formal vector fields. So that's what I'm denoting here. This is called Gelfand-Fuchs cohomology. Wn here is so here X is any n-dimensional complex manifold. Of course, above we were just thinking about 3, n equals 3. But this result makes sense in general. And Wn, I just said it, but Wn is the algebra of formal vector fields.
What's the meaning of the space of anomalies?
So this is the space of.
Is this the central extension?
Exactly. You should think about it in one sense as being the space of central extensions of holomorphic vector fields. Yeah. Another way to think about it, it's like the space of possible obstructions to quantizing the symmetry that I just wrote down. So I wrote down a classical symmetry before. I told you that the chiral boson admits a canonical quantization, this sort of BV procedure, I can quantize it. So you can try to lift these currents to the quantum level. And I'm saying you can't do that, you can only do that in a projective sense. And that one way to think about it is in terms of central extensions.
So you're about to just tell us which one, like, but before you can tell us which one, you have to tell us, like, the space.
The space, yeah, I just wanted to give you a flavor for the space, because yeah, I'm going to use this space to characterize
But
the
now you're
anomaly.
going to tell us, like, a point.
Yeah, exactly. Yeah, I'm going to tell you a point in that space. I stated this result in the case that X has smoothly trivializable tangent bundle. We're only going to care about that case from now on, because I really just work on C to the n, or punctured C to the n from now on, but it also, there's a similar result that holds in general that I can explain to you if you care. So like I said, we're just going to work on affine space for now, because this is where a lot of the familiar objects exist, especially within the context of vertex algebras. So when I'm on C to the n, we can identify that cohomology space that I just wrote above as a certain cohomology of formal vector fields, a certain Gelfand-Fuchs cohomology. And it turns out to be isomorphic to, in dimension n, the 2n plus 1 cohomology. And there's a nice, there's a beautiful result going back to Gelfand and Fuchs, which identifies this space here with the space of characteristic classes, universal characteristic classes in dimension n of a certain degree. Here the degree is 2n plus 2. And what's going on in this isomorphism, and I'll try to explain this, well, I'll sort of cryptically explain it later on, but what's going on in this isomorphism here is very closely related to the Riemann-Roch theorem.
Can you just say, like, in one or two words what Gelfand-Fuchs means?
Oh yeah, so it's just the Lie algebra cohomology of formal vector fields. But when I say that, I mean that the cochains are continuous, so that's what Gelfand-Fuchs means. Because these are infinite dimensional Lie algebras, so I have to require
It means like some sort of continuous Lie algebra.
some continuous Lie algebra cohomology, yeah, exactly. It's like obvious, the topology I'm always just using like the adic topology on formal vector fields, and you just require the cochains be continuous for that. Okay, so n equals 1, so that's ordinary chiral CFT. I'm telling you that the anomalies are identified which H3 of formal vector fields on the line. Well, this is isomorphic to H4 of BU1, that's this general result here. There's only one object there. It's the square of the first Chern class. So this square of the first Chern class is really what's behind the Virasoro or the Weil anomaly. And you can write it as a local functional. So I told you, I'm describing anomalies sort of abstractly here. There's one way to think, there's a more explicit way to think about anomalies, which is in terms of actual functionals on the fields, which in this case are vector fields. And you can identify, there's a correspondence that I worked out which can identify classes here with explicit local functionals. And in the case of n equals 1, the square of the first Chern class corresponds to this quadratic functional here. And that, if you squint, so J here is the Jacobian of a formal vector field, and if you squint and just work on, if we're just working on C, then this is just the same. If I write mu as f of z dz, then this becomes just dz f dz squared. Which is a familiar formula of the Virasoro cycle. So it's that famous one that you find in CFT that involves 3 derivatives. 1, 2, 3. So that's behind the usual Virasoro central extension. Now in n equals 3, the case that I care about, I have holomorphic vector fields on C3 now. The anomalies are controlled by H7 of W3, which is H8 of BU3, and there's 4 things there. I just want to emphasize this correspondence between anomalies and characteristic classes is really indicative of probably things you've done all the time, like really what's going on behind the scenes here is some index theorem, right? I'm computing some index. That's why I said Riemann-Roch was important. This is all about the index. Here it's of the, not the Dirac operator because there's no Dirac operators, but there are Dolbeault operators. So what's going on here is the appropriate combination of these classes here it's easy because we just have one, but the appropriate combination is controlled by the index of some Dolbeault operator. That's one way to characterize these anomalies explicitly. I can also model, this is not so important, but I told you there were 4 classes in dimension 3. Those are 4 representatives for them. I don't want to spend too much time on them, but you can sort of see the analogy with complex dimension 1. They're similar looking classes. The feature of all of these is they're not quartic. What that means is that, you know, we know this thing corresponds to an honest central extension of vector fields. The fact that these are all quartic means that they are really modeling not in strict Lie algebra, but an L-infinity central extension. So these are modeling central extensions that have 4 inputs instead of just 2. So that's one remark. But yeah, their precise form is not going to be useful for us for this talk. Now, Ben asked about the specific class that you see from the chiral boson, and this is just computed by Riemann-Roch, so I'll just state what it is. The anomaly is the following. So it's the 8th component of the Todd class minus the 8th component of Todd times the universal Chern character of the tangent bundle. So you think about this as being something in H8 and U3, so it's a combination of those universal characteristic classes that I just wrote down. You can work it out if you're bored. It's not going to be important. I will say, though, that it totally checks out with anomalies in the physics literature. So there's anomalies, they're not working with a holomorphic twist, but anomalies are one of those things that are typically preserved by twisting. It's, if you have an anomaly in the physical theory, you're still going to have an anomaly in the holomorphic twist. And in some sense, that one is determined by the anomaly in the physical theory. And it's compatible with those results in physics as well. I'm only saying that because I told you that from supersymmetry, this hierarchical boson is just a substitution for the 61, 0 theory. And people know how to compute the anomaly for that theory. So I want to get to the actual thing called the Virasoro algebra, because what I've been talking about is sort of abstract. I'm talking about like a sheaf of vector fields on an arbitrary threefold in many cases. I worked on affine space briefly just a second ago, but really the Virasoro algebra is about a punctured disk. It's about an extension of vector fields on a punctured disk. So in higher dimensions, the punctured disk has an important feature that it's no longer affine. So that's one big motivation for considering not just sections of the holomorphic tangent bundle, but really its derived sections. You're going to get a much more interesting algebra, Lie algebra. It's a DG Lie algebra, differentially graded Lie algebra. Because if we just took, because it's by a result in complex geometry called Hartog's theorem, if I just looked at ordinary sections here of the holomorphic tangent bundle, it would be the same as sections on just the unpunctured disk. So you're not getting anything new. But if we work in a derived sense, this full DG object is much richer. And as I said before, the anomalies, they do correspond to central extensions, and at this level, what we find then are 4 separate central extensions. Sorry, this n should be 3 here. I talked about, this is a 3-dimensional version of the Lie algebra. N should be 3. And I get a 4-dimensional space of central extensions. So any of those anomalies translates to a central extension that I just wrote down here, that I'm writing down here. The way to translate between those integrals that I wrote before and these sort of more algebraic central extension is just to replace those integrals by the residue. Which you sort of know from a lesson here. Like, if I was thinking of mu as just a general section of vector fields on a Riemann surface, I could write down this formula. But the actual Virasoro cocycle is about taking the residue. So it's pretty simple. You just think about the residue instead of integration. And of course here it's, a higher residue, which you can think about as being the surface integral over the codimension 1 sphere in C3. So as a consequence of some of the things I said, we get the following statement, namely that the space of local operators in the holomorphic twist of the 1, 0 tensor theory is naturally a representation for one of these higher dimensional Virasoro algebras. It's no longer unique because I have 4 different ways to centrally extend. When I write here, it's a very specific central extension, the one corresponding to that anomaly that I characterized before. One nice consequence of this is that objects that are familiar from supersymmetric field theory, namely, here I'm going to focus on what's called the supersymmetric index of the 6-dimensional theory on this very simple manifold, namely the 5 sphere across the circle, takes an algebraic form. It's an algebraic invariant of this representation, namely the character. So I told you there's a representation here. For the higher Virasoro algebra, I can compute its character as a representation. And I claim that you exactly see this supersymmetric index. And that works for more than just the 1, 0 tensor theory. This is a statement that's true for the holomorphic twist of any 1, 0 theory.
Is S5 times S1 a complex manifold?
It is, yeah. It's not Kähler, though. So it's what's called a Hopf manifold. So you take it's exactly this geometry. So you look at C minus 0, but then you push it out. You push it out by a copy of the integers. Something like this. Yeah. Where there's like, instead of, this is like a presentation for an elliptic curve. So here there's really like 3 moduli parameters, Q1, Q2, and Q3. Yeah, so you can understand this even purely in terms of the holomorphic twist. You can relate the character to the partition function on this Hopf manifold. And that actually gives you a little bit more structure because it tells you sort of manifestly that the partition function sort of depends in a very nice way on the complex structures of Hopf manifolds. This is something that's not completely obvious from like the physical perspective. So it's a good question, like, is there an analog of like modularity or something here? Like we have for ordinary CFT.
So the answer you're about to tell us is going to have 3 parameters QI.
Oh, I'm not going to tell you this. I could write it down if you want. It's not going to mean much.
Okay,
but,
if you didn't tell it to us.
It has 3 parameters, Q1, Q2, and Q3. Yeah. That's right. Oh man, I should have wrote it down now. I didn't because I feel like it wouldn't have been fun. I'll do it next time. So where does this, there's an explanation for the symmetry that I just explained, the Siegel-Sugawara construction for the higher chiral Boltzmann. And this is justifying the appearance of holomorphic vector fields. And this is a big strengthening because it's going to tell us that in fact the twist of any 1, 0 superconformal theory has such a symmetry. And this is recent work with Fabian Painter, Surya Raghavendran, and Ingmar Severi, where we've shown that the holomorphic twist of the full 1, 0 superconformal, physicists call this the Weyl multiplet. So you should think about this as being the, it's not a field theory, but it's an object which controls the superconformal symmetry of a theory. So it's an analog of holomorphic vector fields in the same way I had before. That was a symmetry of the holomorphic twist. So there's this enhanced object called the 1, 0 Weyl multiplet. And you can contemplate its twist, and in fact, it's exactly holomorphic vector fields. So what this tells you then is if you, a superconformal theory is one which has this multiplet as a symmetry. So if you twist it, manifestly, you're going to have holomorphic vector fields as a symmetry. So it's no surprise, the formulas that I was writing down before. This is a local statement that we made. A global statement would be very nice. So we only were able to show this on R6 or C3. A global statement would be also very nice. That works for any complex threefold. Of course, we can write down the symmetry in any complex threefold, but we don't necessarily know it comes from a twist. That's all I'm saying. Okay, so in the last 15 minutes, I wanted to move on to M5 branes and a certain exceptional symmetry that that extends this symmetry by holomorphic vector fields. So the theory on an M5 brane in M theory is known to be n equals 2, 0 superconformal. Before we were looking at 1, 0. And we wish to study the holomorphic twist of this object here. Sort of a hint as for the flavor of the holomorphic twist can be gleaned from 11-dimensional supergravity, where we've characterized the twist there. So what we've shown is that the low energy limit of M theory, namely 11D supergravity, admits a holomorphic twist. And it can be placed on any 11 manifold of the following form. So it's not strictly holomorphic because it's an 11 manifold, there's no complex structures on a 2-dimensional manifold, but it's sort of like partially topological and partially holomorphic. So it's holomorphic on what's either S1 or R, and it's topological on either S1 or R, and it's holomorphic on the remaining part of this 11 manifold, which is required to be a Calabi-Yau 5-fold. So that this is an admissible geometry that you could twist 11D supergravity. And at least when Z is just affine space, we've characterized the twist of this object, which I'm not going to spend time on. But for the context of studying 5 branes, though, so those are like defects in this 11-dimensional theory. A natural choice for this Calabi-Yau 5-fold is the following. Namely, the total space of the following rank 2 bundle, holomorphic rank 2 bundle over an arbitrary complex 3-fold. And I chose this, so what that says is I've chosen a square root of the canonical bundle of the 3-fold. And the point is that this thing is automatically a Calabi-Yau 5 because of the way I chose the square roots there. So that's an admissible geometry to study 11D supergravity, twisted 11D supergravity. And the reason I'm choosing that is because 5 branes are very easy to describe. They wrap a 0 section. I don't know why that says C. That should be an X. Oh, sorry, I'm not there yet. Anyway, so that's the correct geometry. Now, we characterize the holomorphic field theory, which lives on this M5 brane. The reason I introduce this is because these square roots will appear in this description. So the holomorphic twist, well, I'm gonna describe it in such a way that I still preserve parity. So this parity is the leftover of the usual parity between bosons and fermions in a supersymmetric theory. So there's an even part and an odd part. There's bosons and fermions still. And it has the following space of fields. So you recognize immediately this higher chiral boson. That's this closed 2 forms, holomorphic closed 2 forms. And then there's also a remaining piece, which take the form of fermions. And you can identify those also with a certain 1,0 theory. It's called the hypermultiply. So it's another very basic free 1,0 theory. And this is the description of the twist of that object. That should say X. So it's just a modest enlargement of that chiral boson theory that I have. So this is like a supersymmetric. You think about this as a more supersymmetric version of the chiral boson. So the natural question is, what's a extension of holomorphic vector fields, which I know are a symmetry. In fact, I know holomorphic vector fields are a symmetry for this and for this. They still act on the hypermultiply just by Lie derivative. The action here was more complicated. I wrote that down in the previous section. But is there more that acts? Is there a bigger algebra that acts? And we answered that question to the affirmative. The twist of this 2,0 theory has, and we wrote down an explicit symmetry of the following Lie superalgebra. It has an even and an odd part. So the even part, familiar holomorphic vector fields, just like before. And now you also have these SL2 currents as well. So SL2 valued in holomorphic functions on the 3-fold. So this is really like a version of like a Kac-Moody or flavor symmetry that's around, if you've seen that before. It's really a remnant of the R symmetry, not flavor symmetry. So this is the part of the R symmetry that survives. And then there's an odd part as well, which looks like this.
Extra stuff, can you think of it as coming from the extra dimension?
What is that?
The SL2, can you think of it?
Yeah, exactly. That's right. So the SL2 is exactly the symmetries of this Calabi-Yau 5 here. So the rotating the fibers on this Calabi-Yau 5 is exactly the same SL2. That's a really good point. And as you know, like it's the same picture as in the untwisted theory, like the symmetries of the transverse direction become R symmetry. In the theory, here I'm working at a twisted level, so the symmetry in the transverse direction is a little smaller. It's SL2 instead of, what is it, usually SO5. So it's like broken down a bit, but it's still the sort of parallel picture. Yeah. That's a really good point. I'm not going to describe the odd symmetries at all. So this is like actually later on when I mentioned AGT, the AGT deformation is a specific section of this bundle here. So it's like a further, it's a certain Mara-Cartan element of this Lie algebra, and it takes the form of some odd section here. But I'm not going to talk about it too much. I will point out the bosonic part of this symmetry. So you recognize the single Sugawara vector I wrote down before. So that involves just the closed two-form field. Like I said, you can also take the Lie derivative of the fermions, and that looks like this. That's a Hamiltonian action because here I'm using it's a symplectic pairing between the size. Size is valued in a symplectic representation, C2. And then there's also this R symmetry that's around as well, which just acts on the fermions, as was pointed out. So that completely describes the currents associated to a vector field and a SL2 holomorphic connection, if you think about it that way. So just like before, at the quantum level, this is no longer a symmetry. It's just a projective symmetry, so there's some central extension. We can describe the central extension. I'm going to do it sort of loosely here. Just the bosonic part. So that is, I just mean the part of the anomaly which depends on the even fields that I just wrote down in that exception. Oh, I forgot to say a very important remark that's pretty fun. So it turns out that this Lie superalgebra, I didn't describe the Lie brackets at all. Vector fields, you can sort of imagine how they're acting everywhere by Lie derivative. SL2 is rotating this, as was pointed out in the obvious way. And then there's some interesting brackets which take two odd elements to an even element, which I don't want to describe. But I want to point out that when X is C3, this Lie superalgebra becomes one of these exceptional infinite dimensional Lie superalgebras that was discovered by Katz, and it's called E36. This is really, E36 really just refers to the value of this thing on C3. Really it's the value on the formal 3-disk and not the macroscopic 3-disk, but it's loosely the same. So you really should think about this as being sort of like a sheafified version of this exceptional Lie superalgebra, E36.
Is there a way to make that precise? Like if I just know E36, then I can globalize it over any complex?
Yeah, I mean, the way Katz writes it even is, in fact, in this form. Like, he writes it as, like, holomorphic vector fields, SL2 valued, like, power series. So, like, everything has an obvious generalization to a vector bundle. And, like, we just observed that you could do that. Yeah, it just works. Like everything is, like, actually holomorphic diffeomorphism invariant. The brackets are, like, yeah, it doesn't depend. So it globalizes in an obvious way, and sort of in a very natural way, yeah. So I just want to describe the bosonic part of this anomaly that arises from quantization. So the bosonic part, it's going to involve these characteristic classes that I wrote down before. That's part of this Gelfand-Fuchs cohomology, describing the extension of the vector field part. There's also a term which describes an extension of that part involving SL2. And I mentioned before, it looks a lot like you should think about it in analogy to the Kac-Moody algebra. And really, this Tartly anomaly is exactly the central extension that Fayante, Hennion, and Kapranov discovered as generalizing the Kac-Moody algebra to higher dimensions. So this SL2 part just describes a central extension of this holomorphic functions on SL2, or really its derived section. SL2 tensor. Really, I should work with derived sections of the structure sheaf. When X is punctured C to the n again, or here is C to the 3 minus 0, this is what Fayante, Hennion, and Kapranov call the higher Kac-Moody algebra. So inside of this algebra, this big exceptional algebra, after centrally extending are one of these higher Kac-Moody algebras that those authors study. And there's also a mixed term in this anomaly as well that I won't describe. So terms that involve both these characteristic classes here and this SL2 part. I want to say one more thing is that we haven't proved this, but we expect this exceptional symmetry to actually have a unique anomaly. And that's a universal statement. So just like an analogy with the usual CFT picture where there's always a unique thing you mean by central charge, it looks like you should have more around because there's more fields around, you should have more central extensions, but in fact we actually expect there to be a unique anomaly. So in other words, only a very specific combination of these characteristic classes will appear in general for any central extension of E36. Again, on punctured affine space, I was doing things at the sheaf level before, but if I just look at the global sections over punctured affine space, before I told you that was the right thing to think about in the context of the higher dimensional Virasoro algebra. So if you do that in this case, you're essentially extending this exceptional thing that I talked about before, and you get some super symmetrized version of this higher Virasoro algebra. And this is the thing I'm calling the Dolbeault Virasoro algebra. I'm now going to justify that in the last slide. But as I was just pointing out before, like this exceptional thing contained a lot of interesting objects. So like E36 was contained in here. This is just like the positive part. So like an analogy with the ordinary Virasoro algebra, the positive modes are just a copy of vector fields on the disk. So this is like the analog of vector fields on the disk. This contains also this Fante, Hennion, and Kapronov algebra, SL2 valued derived sections of the structure sheaf. And it also contains this bosonic Witt algebra that's just holomorphic vector fields on punctured C3. So this thing contains a lot, and we're studying the central extension arising from this anomaly. Okay, I'll wrap up soon. So this AGT deformation, as I mentioned before, this is specific to a geometry which is C cross C2. That's what I wrote there, that's being blocked out. So here C is a Riemann surface. And in this geometry, there's a deformation or simplification of this theory. And this is called the omega deformation, or the omega background. And so sort of roughly what it does is it localizes the theory in space-time to just the point inside of C2. And this is done by taking the homotopy S1 times S1 fixed points where the S1s are just rotating each copy of the complex plane. That's this C2. And this omega background leads to a very beautiful mathematical statement going back to, discovered independently, of course, by Nakajima and Broniewski, which is to say that the cohomology of the space of states of this theory, which in this equivariant sense you can understand as the S1 times S1 equivariant cohomology of the Hilbert scheme of points on C2. And the mathematical statement is that this object has the natural structure of a vertex algebra. And that comes from the fact that the theory in this plane, in this direction here, is still holomorphic. So it's still holomorphic here. So this is this famous result of Nakajima and Broniewski in part that discovered this vertex algebra structure there. And in fact, in the case that I'm talking about, this case of the twist of the 2,0 theory, if we run this procedure, what you find is really the chiral boson vertex algebra. That's what this is. That's all this is right here. The original vertex algebra that I introduced on like the second slide. And this is sort of one of the statements I mentioned at the beginning of the talk. This exceptional symmetry that I've been talking about becomes, in this twisted omega background, that is when I place the exceptional symmetry on this geometry and then I deform, it becomes exactly the usual Virasoro algebra. And there's some function that this central charge depends on this anomaly in some way, but because of this conjecture that we're hopefully close to showing that there's a unique space of extensions in both of this case, so it's just about matching up a single number. to arrive at a universal statement. But in the case of the free theory, we can just compute the central charge directly. So that's the statement about exceptional symmetry deforming under this omega background to the usual Virasoro. And now I can finally motivate my terminology Dolbeault Virasoro. So remember, recall that this exceptional symmetry could be placed on any threefold. Now, if I take the threefold to be a complex surface now across C, then sort of opposite to what I was just doing a second ago. So now I'm assuming that I have an interesting behavior in this two-dimensional complex direction. Then part of the AGT correspondence, and going back to Nakajima, it tells us that there should be a deformation of our object, which acts on the de Rham cohomology of the Hilbert scheme on S now. But before turning on this deformation, this is not exactly the omega background. It's what's called it's actually a further twist. It's like a further topological twist of the 6D theory. But before turning on this deformation, what we expect is that this de Rham cohomology that appears here should just be replaced by the Dolbeault cohomology, and we're left with a statement like this, where this exceptional symmetry on C cross S should act on the Dolbeault cohomology of the Hilbert scheme of S. And by Dolbeault, I mean like Del-Bar cohomology with coefficients and holomorphic de Rham forms. So of course, when S is proper, there's no difference. This is just isomorphic to de Rham. So I didn't get much from this, because if S is projective, this is all projective. My Hodge to de Rham spectral sequence collapses, so I don't really get anything new. But the thing I want to point out is that there's a generalization of this algebra, which comes from studying M theory on a slightly more exotic 11 manifold. And it has to do with basically introducing the dependence on a line bundle. So what you do is you fix a line bundle over your surface. You look at this following rank 2 bundle, which is L plus its Serre dual. So this thing's actually automatically Claviau. It's a Claviau surface, Claviau threefold. In fact, I have this extra copy of C. The 5 branes are wrapping the 0 section there in this copy of C. So this is somehow still part of the R symmetry data. I'm just generalizing the R symmetry data. And what we find, and this is really at the level of a conjecture still, but what we conjecture is that this exceptional symmetry in the presence of this data of a line bundle acts on the Dolbeault cohomology of the Hilbert scheme of the surface with coefficients in some holomorphic vector bundle now. And this is a holomorphic vector bundle which is defined in terms of the line bundle L. It's called the tautological bundle. So strictly speaking, this tautological bundle is defined for every Hilb n, and this is just a direct sum of all the Hilb n's. So it's just like a stratified thing. But I'm stating it sort of loosely like this. But this motivates the description of the terminology Dolbeault Virasoro, because it's the Dolbeault Virasoro that's really a central extension of this object. Okay, I'm sorry for going a few minutes over, but I'll stop.
Thanks for a great talk.
Thanks.
So the Nakajima-Granovsky result is about the cohomology, equivariant cohomology of the Hilbert scheme and the structure of a vertex algebra. Is the Dolbeault cohomology of the Hilbert scheme supposed to have some like enhanced structure?
Yeah, no, actually a similar statement here. So the vertex algebra structure just comes from the fact that I have this copy of C. So I could actually, another statement would be that this object here also has the structure of a vertex algebra.
So you can enhance that too.
Yeah, exactly. That's right, yeah. It was just important that you have this copy of C around. So in fact, what we really have, if I didn't choose a decomposition like this, what we really have is like a 3-dimensional vertex algebra, because we have 3 holomorphic directions. But to try to make more concrete results, you could try to, this is what people have been doing for a long, long time now, just try to decompose, make some of the directions compact, so that you really just have a more understandable structure there. But I think this is really a new vertex algebra even. Like, I don't think this has really been written down by Nakajima and the like. I think this is some sort of new vertex. I don't know how interesting it is, but It's at least a structure I haven't seen written down yet.
The S is like a product of elliptic curves. So I'm just trying to think what's the simplest complex surface.
Yeah, even then I just don't know if it's been, yeah. I imagine it has been in some way, but I should do more literature search. I found, so I have found formulas for Poincare polynomials of this object here, and we're right now working towards actually recovering those from the point of view of these characters of E36. So that looks like it's working out nicely, but we haven't yet written down the full vertex algebra structure, but we know it should exist implicitly.
Can you say where this algebra E36, so what's exceptional about it? Is there some classification?
Yeah, so Katz classified what he called, what are called locally compact infinite dimensional least superalgebras. So these are all, locally compact just means that you basically look like power series. That's what locally compact means. And what he found was that him and collaborators found that they basically exist in some number of families, typically. Like one family would just be vector fields. So like vector fields on a disk, on an n-dimensional disk, that's like one family of infinite dimensional least superalgebra, locally compact infinite dimensional least superalgebra. Another one is like Hamiltonian vector fields on a symplectic disk. So that's like another family, for example. So there's like 5 or 6 of these that exist in families, even in a super sense as well. And there's like a list of like 5 or 6 that just don't fit into this categorization. And E36 is one of them. Yeah. Sort of amazingly, another one that doesn't fit into the pattern is an exceptional algebra he calls E510. And this somehow controls the twist of 11D supergravity. So somehow M theory is picking out these exceptional least superalgebras that Katz found, and I don't know why.
So exceptional.
It's just an exceptional theory, yeah. It should be related, there's this old story that between exceptional finite dimensional groups and M theory, I have no idea how it's connected to this, but it sort of feels like it should be.
Let's thank Brian again.
Thanks.